Good evening, everyone. Welcome to the Sigma meeting for February 2022. For those of you who don't know me, my name is Pete Sherman. I'll be your MC for the evening. I'm the chairman of Sigma, and I would like to start by welcoming not just the Sigma members we have here tonight, but also the affiliated members we have from HAS, which is Highland Astronomical Society, Aberdeen Astronomical Society, Cairn Gorman, Caithness Astronomical Groups, and also North Bromwell, and any first-time visitors that we may have here as well tonight. You're all very welcome, and I hope you enjoy the evening. Just before we get going tonight, I want to start with some good news, and that is that this may be the penultimate online meeting. We are actually planning, your committee is working hard, very hard, to get us back to physical meetings for April. Okay, so hopefully we'll be back in Lambride for the meeting in April. I won't go into too much detail just now. You can read about it in the newsletter, and I'll be updating you as things sort of progress in the coming weeks. What I will say though is that we are planning a practice meeting. It will be run like a proper meeting, okay, but it will be in the small hall. Reason for that, once again, is in the newsletter. The main hall may not be available for us. If it is, we can move to the main hall, but it may not be available at the time. And that's going to be on Saturday, the 12th of March at 7:30 p.m. usual time. But it's a Saturday, not a Friday. The reason it's a Saturday is because it gives the committee a little bit more time, not having to come home from work, so we can get set up properly and keep things as well, get things organized as safely as we possibly can. Unfortunately, I'll be your speaker for the night, so you have to put up with me. Okay. No, what I'm going to do is I'm going to do the tour of the solar system and beyond. This is the one we sort of put out to the outreach we do, and it's a nice basic talk, and then we can just relax a little. Well, you can relax a bit, I won't, and we can hopefully have a good evening. We are planning to have the tea break as well as normal. Plans are still coming together how we can do this safely, but we will get the tea break going somehow, because I say that's an important part of Sigma. We can all have a chat together and get together for our first time in a long time. And if conditions allow, we can actually do some observing if the weather's any good as well. So once again, there'll be more information on this in the newsletter, once we sort of finalize a few things. But your committee really does need your help on this one, because we're in the small hall. We are going to be limited to numbers. It's going to be about 30 people. So Mick will sometime in the next week or so be sending out a registration email for this. So you'll have to register for the actual meeting. Okay. Obviously, if what we're going to ask you to do for this meeting as well is to actually, if you can, take a lateral flow test. And if for any reason you can't make it, let Mick know, because we'll have a reserve list of members who we can put up into your place. Okay, but more about that, it'll come on later on. Anyway, helping me tonight in the background, I've got Rich and Mick, who are your Zoom co-hosts. So if anything goes wrong with me on the interweb, they will take over and run things. Also helping me is Stuart Brooks, who will be doing space news in the second half, along with Mick, who will be doing the morning sky at night. And I'll have a little bit more news myself about Sigma at the end as well. Also there, Rich, Chris can't make it tonight. Unfortunately, he's down in London. He's in the smoke. So Rich will be handling the Q&As. Okay. Now we're talking about the questions. We'll ask you to put your questions into the Q&A. Anyone who's new to Zoom, if you get your pop-up bar come up, you'll see Q&A. We ask you to put any questions in there, please, not in the chat. Firstly, the chat's going to be turned off during the talk. And also, if your questions go in the chat, they can easily get lost as that scrolls down. Okay. Now, if you have any questions for Oliver about the content of his actual talk, if there's something you don't understand, you're more than welcome to put that question in, as he's talking, and Rich will try and ask it over to Oliver to, so Oliver can explain a little bit more before he moves on to the next stage. Okay. And also, if you've got any general questions on his presentation, please put them in the chat as it's going along, and Rich will monitor it, and he'll then ask the questions at the end. Okay. But if there's anything you don't quite understand, please put it in the chat, and we'll get Oliver to just explain a little bit more for you. Okay. Okay, and don't forget, after this meeting, we're having the members gathering, which I think Oliver is going to come along to as well. So if you've got any other questions, he will happily answer them as well for you then. And I say the link for that is actually in the newsletter, but it will go into the chat at the end of this presentation, and at the end of the evening, and just click that link and you should take you straight over there. Okay. Right, so this is how a Sigma meeting works, a meeting brief. We have the main talk, which tonight is going to be by Oliver. Rich will be doing the Q&As. Then we have our little 10-minute break. We always have a 10-minute break in Sigma. You can get yourself a cup of coffee or a whiskey or whatever you want to get. After the break, we've got the space news with Stuart Brooks, Morning Sky Night with Mick, and I'll say a little bit of club news with myself. So on to our guest speaker for tonight. Tonight we'll be looking at how astronomers can study the surface of rocky exoplanets without actually being able to see them directly. That's with Oliver Herbort. Oliver, who is actually joining us from Graz in Austria tonight. When we had our little practice run on Sunday, Oliver said how disappointed he was that he couldn't get up to sort of Moray and actually be with us tonight, such as his love for the Highlands. He keeps telling us about this. And also he's got a love for whiskey as well. Well, more about that in a moment. Okay, I must admit that I'm a little bit envious that I'm not in Austria, because I fell in love with the place when I went over to Tyrol a few years back, and must get back there again one day. And say when I went there, I found it was very much like the Scottish Highlands, but with much better weather. I thought. So he's joining us from. I'm going to give this a go. I have hyphenated it. The Institute für Weltraumforschung. Close, nowhere near.
Institute für Weltraumforschung.
I knew I'd get it wrong. Institute
was all right. Was intelligible.
Institute for Space Researchers, I believe it is, isn't it? Okay.
Exactly.
So please welcome Oliver Herbort. Oliver gained his bachelor's degree in Germany between 2013 and 2016. He had an MS seminar in Poland for 1 year. He gained a Master's of Science and Physics back in the George August University of Germany in 2018. From then, he has been in St. Andrews studying atmospheres of exoplanets. And I say another passion of Oliver's is malt whiskey. In fact, he is the charity officer for the St. Andrews Malt Whiskey Society, which is a charitable society, and all the proceeds for that charity, for their charity events, goes towards water aid, which is quite good, really. So whiskey and water, I thought. There's only one thing goes with whiskey, and that's either more whiskey or a little bit of water.
Yes, and there's a reason why it's called the water of life.
Exactly. Aqua Vita. So for this reason alone, we will one day have to invite you back up, Oliver, and actually get you into the Malt Whiskey County, and we'll take you around a few of the sort of distilleries. But for now, please, everyone, give a warm welcome all the way from Austria, Oliver Herbort. Over to you, Oliver.
Thank you very much for that kind introduction, and hope you can see now my slides.
Yep, got it.
I just check this to the side that I can also fully see my slide. And yes, as it said, my talk is about how we can actually go from clouds to crusts or from atmospheres to crusts, how we can actually infer knowledge on the surface of rocky exoplanets. As not everybody here is really working on exoplanets on a day-to-day basis, there will be a bit of an introduction of like what rocky exoplanets are, going further to what we actually want to model in our work, to go where can we actually find water or whiskey, and then what kind of clouds are on those planets, how do they look like, how can we characterize these atmospheres, and then some take-home messages at the very end. So let me start with one of the images that was already on the first slide, on the introduction slide. Just many different planets, actually most of them relatively small in this image at least, that we already have found outside of our solar system. Those are so-called exoplanets, so planets that are not in our solar system, but somewhere else, orbiting some other stars. We see here on this slide just some planets that are familiar to us: Earth, somewhere here, and then Mercury down in the bottom right corner, to just get a grasp of the rough scales of these planets. But not all planets are similar in scale to Earth, but if we actually look at the full image of this plot, there are super many gas giants out there that are similar to Jupiter or completely different to Jupiter because they're so much hotter or so, but they are not the topic of today's talk. Today's talk is actually focusing on rocky planets, those that kind of have a surface, something like Mars, Venus, Earth, or Mercury, for example, also a bit larger. So not just that the sizes of the planets are different, but also the stellar systems are completely, or can be completely different at least. At the bottom here of this plot, we see our solar system. The planets a bit larger than they should be. So Mercury, Venus, Earth, Mars, we all know them in their respective orbits around the sun in the very center. And if we compare this, for example, to one of the most famous rocky exoplanet stellar systems, which would be the TRAPPIST-1 system, which if we actually put it in the actual scale of our solar system, it's this tiny few rings down here. If we enlarge it by 25 times, we can actually see that there are 7 rocky planets orbiting that pretty small star. And just because that star is so small, the temperatures of these planets are also much, much lower. So some of them might be potentially habitable. What does habitable mean? I'll come to that later in the talk, but roughly there could be water on some of them. If we compare this to Jupiter, we see actually that it's not the same scale, but more like Jupiter in scale than our solar system itself. So it's somewhere in between of Jupiter and the solar system as a system itself. But that much said to this one individual stellar system, but this is one of the plots that basically every exoplanet talk has to show. What do we see? We see the orbital period of many, many different planets. So how long it takes to go once around the host star versus the planetary radius, so how large the planet is. And on this plot, we have multiple thousand planets, by now roughly 5,000 planets that we know of. Not all have a radius measurement, but some, and they are plotted on here. And we already see there's a huge variety of them. Earth would be here at 1 Earth radii. It's a very useful unit for describing at least rocky planets, whereas up here there's more like gas giants. But actually, in order to characterize whether we actually have a rocky exoplanet or not, just having a look at the radius is not enough. We actually also have to look at the mass of the planet. And that's what we do on this plot here. So radius over mass here on the x-axis. And there are roughly 5,000 planets that are confirmed to date. Over 1,000 of them have actual measurements in mass and radius. And if we put in Earth, we have here Earth at 1 Earth radius and 1 Earth mass, but everything is considered rocky. That is roughly around 8 Earth masses or less and 2 Earth radii and less. Those are these 2 lines in here, this bottom left corner. And there we see, yes, there are 1,000 planets in this whole plot, but not that many in the bottom left corner. So it gets populated now, every now and then, but still that we don't know that many of them, a couple hundred at most. And one other interesting part that one can see and here already is that there's a significant gap up here around somewhere like 5 or 6 Earth radii. And that's basically the gap between some where we go up to the gas giants. So everything above that is actually a gas giant. Below that, it's some Neptune-esque planet down to the rocky planets down here. One interesting question that you may have right now is, yes, nice, those planets are out there, but how do we actually measure their actual size? How do we get there, put a scale on it, measure the radius or diameter? Of course, we can't do that because they are quite far away and we can't just put the planets on scale. So we have to do some observational tricks to actually do that. And that's what I'm explaining next. The first thing is the transit method. For many, or actually probably most hobby astronomers, one is familiar with Venus transits, or so when Venus is just going in front of our sun and blocks a bit of the sunlight, or in a bit larger scale when we have a solar eclipse, when the moon is actually eclipsing the host star. The same thing is happening when we observe some planetary systems out there, and if the actual planet moves in front of the host star that we see here at the top while it goes around, just dims a bit of the light, and then when it goes around on the backside, goes back again behind the star, and that's then the secondary atmosphere. So primary atmosphere, the big dip at the front, where you can actually only see the star minus the planetary shadow. So basically, part of the light is being blocked, and then on the night side we see just the star itself, not on the night side, on the secondary transit. Well, while just before it we see the day side of the planet, which is a bit hotter than the night side, so we can actually also see here a slight difference between the actual planet, where we have the day side emission versus no emission at all. So that's how you can basically get information about how the day side looks like, at least in theory. Of course, all these observations are not as detailed as you see here on this plot, but rather just one point source. And then the second method, because from the first one we get the size of the planet. When the planet is orbiting around the host star, it's not only orbiting around the host star, but the host star is also moving around the general center of mass of the stellar system, and therefore moves a bit. Some spectral lines are a bit shifted, Doppler shifted, red shifted when the star moves away, blue shifted when it comes towards us. And with the help of Kepler's laws and knowing of the periodicity, how long it takes to go around, we can actually measure how much the planet has to weigh. So we can know the mass, we know the diameter, so the radius, so we can know the overall density. But that does not tell us yet what this planet looks like. Does it more look like this uninhabitable, completely bone dry planet, or the moist, wet planet with some nice water clouds on the planet and some lovely water oceans where we could live on? So we don't know that yet. And that's basically part of my research. How can we actually get towards these planets? And it's not just a question of wet, dry, but also some planets are looking more like this, like 55 Cancri. It's actually an artist impression of that planet that is so irradiated that it's just so hot that the surface is actually molten. You have a molten magma on the overall surface. So also not really a nice habitable planet, but those are also out there and pretty interesting to investigate. So as I said, during the transit, where the star, now here a bit large and the distance between Earth and the sun, or the star, bit shrunken together, when this planet is moving in front of it, parts of the light go through the atmosphere, and the atmospheric molecules that are in the atmosphere are actually blocking parts of the light. And then we can see some spectral lines. For example, in this sketch, the water molecules block the red lights, while the titanium oxide molecules block the yellow light a bit. And by how much they are blocked, we can in principle tell what kind of molecules are in these atmospheres, because they all have a specific fingerprint in the spectra. That much to the theory that we can get the information about the entire atmosphere, what that is composed of, and potentially also some reflected light from the surfaces. But a planet is a bit more complex, and there is not just a bit of the atmosphere and then the surface, but there's something in between. There are clouds in there, for example, which also scatter light. And because atmospheres are relatively dense, we actually do not probe the entirety of the atmosphere, but just the upper parts of the atmosphere. So just what is the composition up there? And then the big question comes into play. How can we learn something from the upper parts of the atmosphere to the actual crust, how the surface is looking like? And in order to do that, we really have to understand what this planetary system, what this planet is actually doing. And on this sketch, what I have here is just a few sketches of what can happen there. We have the stellar irradiation that will cause some photochemistry going on. So some parts, some molecules in the atmosphere being taken apart and some chemical reactions being triggered by that. That also leads to some atmospheric loss, so that when the host star is basically irradiating the star or the planet, parts of the atmospheres are being dragged way over time. So it's an ever-changing system itself. As I said, we have cloud formation. Well, in Scotland, you know, there are clouds in the atmospheres. Can sometimes be actually quite tricky to look through, so that you don't really see anything above it. But there are also some days, or quite a lot of days in Scotland, where it's cloud-free and very beautiful. And I miss that, and I really want to come back again. But anyways, that's dragging me to a side note. So that's the upper part of the atmosphere, but there are also interaction parts between the crust and the atmosphere itself. There are so-called in and out fluxes. So gases that are going out of the crust into the atmosphere can be done by volcanism or just biology. We humans pump quite a lot of carbon dioxide in our recent history into the atmosphere. That's what we would call an influx into the atmosphere, just a constant amount of carbon dioxide going to the atmosphere. But also in the other direction, there's an outflux, some precipitation happening. The atmosphere is reacting with some rocks, forming new rocks over time. That would be the chemical weathering, for example, or some dissolution or dissolving of some gas species into the water ocean, or dragging some parts of the atmosphere out into the condensate phase. So all of this is happening, and in principle, one has to model everything together and at the very same time, but that's a bit too complicated, and that's why, first of all, we're just focusing for the beginning of the talk of just the atmosphere-crust interaction and what would happen if we would just leave it alone for a long, long time and just keep it there, getting it to chemical equilibrium, so what is most stable. And for that, I am using a model called GGChem, Gleichgewichtschemie, or for those that don't speak German, equilibrium chemistry. It's a code by my supervisor, Peter Woidke, and it works as follows. And that's the sketch on the right-hand side here, where we basically have many, many small cauldrons of all the different elements, and we take a certain amount of each of them. And that certain amount of each of these elements, let's say 1 scoop of hydrogen, 2 scoops of helium. We really like carbon, so we take 8 scoops of carbon, only 2 scoops of nitrogen, and so on. These are basically the total element abundances that we put into our model. And then the model is this box under a given pressure, given weight of the atmosphere, and a given temperature. We set those 2 parameters as well as the total element abundance, and then we calculate what is most stable, or in a bit more theoretical terms, we minimize the Gibbs free energy, basically saying nothing else than what is most, asking the question, what's most stable? And that is not only then giving us a gas phase, but also a condensate phase. So there are parts of the elements that are going to the gas, parts of the elements that go into the condensates. And the gas phase, the elements that mostly go to the gas phase are then called volatile, which means they just are atmosphere loving. There are some siderophile, another great name for that the geologists come up with for these elements, which are more core loving, so they sink into the into the core of the planet itself. But for all what we need here, we have gas phase, we have condensate phase, and we have the total element abundances. And actually, talking about the total element abundance, that's one of the parameters that one can vary a lot, because we don't know that. How is the planet actually formed? What are the elements that we have on a different planet? What are their different ratios? We don't know that. Even if we look on Earth, they are not the same everywhere. Here, an image that I took last year in August on Sky, we have some basaltic rocks, which are different in composition than, for example, if we just hop onto the mainland, just south of Moray, actually, on Loch Nagar, beautiful mountain to hike to, we have more granite-like rocks. And just the appearance of these rocks is completely different. And also the elemental composition is completely different. So if we assume one of these compositions, will get a different result than for the other. And also, not just on our own Earth, we have different element abundances, but also for these kind of objects. Some of you may remember the comet that flew by Earth, I think it's now 2 years ago, in 2020, during the beginning of the pandemic. It's actually a picture taken from myself, from St. Andrews, from Guardbridge. And these comets also have a different elemental composition. And that's actually what I want to emphasize here on this plot on the right-hand side. So all this talk leading up to this figure, where we have the different elements from hydrogen to tungsten actually at the end. And on the y-axis, the different, the element abundance normalized to silica, which just means that we can actually have a nice look on how much they have here. And the different symbols here are actually different sets of element abundances. You can find the Loch Nagar in the continental crust in the crosses, and Kilt Rock on Skye you can find in the mid-oceanic ridge basalt, because it's actually a basalt composition. And then the CI chondrite representative of the meteorite that I've just shown you here. And actually, the chondrite is very rich in these volatile elements like hydrogen, carbon, nitrogen, but also in sulfur. Whereas something like bulk silicate Earth, just the average of everything that we see on Earth, is relatively depleted, so does not have that much of it, of hydrogen, carbon, nitrogen, and sulfur. But also for other elements, there are quite some differences. For example, in iron, the iron content in the chondrites is much higher than for every rock that we find at the surface of the planet. So this is one of the parameters that we put in, one given set of these elements. And then we have the pressure and the temperature to vary. And then we get different gases or different gas compositions and crust compositions. So one wonderful spaghetti plots. And if I would just chuck a bunch of spaghettis to a wall, that wouldn't look too different, but we're more interested in the science. So let's just keep the science plot up here, but this is actual data. So no spaghettis being thrown here, but what do we actually see? And that is on the x-axis, it's the different temperatures in our model from 100 to 5,000 Kelvin. For those that are not aware, Kelvin is just a different unit of temperature. 273 Kelvin are freezing point of 0. So basically, whenever you read any temperature in Kelvin, just deduce 300 and you end up with degrees Celsius. And on the y-axis, we have the different abundances in how much of that given element is in the gas phase. And then each of these lines is one atmospheric species. And this cuddle-muddle, this just stuff that's up here, this mess of lines in the high temperatures, is mainly metal oxides. So something like silicon oxide, chromium oxide, iron oxide. Those would make the atmosphere, if we just vaporize our Earth, most of Earth at least, to something like 3,000 or 4,000 Kelvin, then our atmosphere would be some metal oxide rich atmosphere, which is not too nice to actually live in, but that's what some of these planets like the magma world that I've shown earlier, 55 Cancri, would have rather as an atmosphere, some metal oxide rich atmosphere, which is really cool to think about that is existing out there, or potentially existing at least. If we go to lower temperatures, like still not very low, but like 2,000, 2,500 Kelvin, actually oxygen is dominating this atmosphere, because in rocks, there's so much oxygen in there. There's that if we evaporate just parts of it, we actually have quite a rich, oxygen-rich atmosphere. And then below, we have water in the atmosphere, actually dominating the atmosphere before it is incorporated into the crust. but also sulfur dioxide, carbon dioxide, and for lower temperatures, nitrogen. As we have in our own in our own Earth, our atmosphere is actually dominated by nitrogen. This is the model calculated for the bulk silicate Earth. If you compare this to the CI chondrite, the image stays roughly the same, at least. We again have these metal oxides at the high temperatures, and then followed by water, actually here covering a even larger range in temperatures, carbon dioxide, but also some new species that we haven't seen before, methane, carbon dioxide, and H2, molecular hydrogen, and also atomic hydrogen. And those are direct results of just having more of these volatiles in our set of total element abundances. So when we compare these two to each other, we see that the water level drops at the bulk silicate Earth already at around 900 Kelvin, whereas for the CI chondrite it's dropping at around 400 Kelvin. So there's a huge difference in there. And the question is, where does this water go? Does it go into the crust? Does it form a lovely water ocean that we're actually looking for, so that we just have to find, oh yeah, there's water in the gas, so there's a water ocean? And we're going to see that in the next slide, where we actually look at where the hydrogen is in the lower temperatures. Here, 1000 to 100 Kelvin, so just the lower part of the temperatures, and plotted only the hydrogen-bearing molecules and condensates. As I said, water dropping in abundance at around 900, 800 Kelvin, and then every hydrogen atom is basically incorporated in these two quite complex condensates, which are called soda phlogopite and phlogopite, or hydrated rocks. So rocks that actually include some OH groups into their lattice structure, and that will then look like this small phlogopite that is also found on Earth in various places. So we actually do not have any water condensates because it's all kept in the rocks, and that's actually the more stable form. Most of us probably know that when you have a bit of clay laying around and it's dry, and you pour some water over it, the clay rock will actually just incorporate the water, just soak it up. If you pour more and more water on it, you will have a puddle on it at some point because it's saturated in water. And that's exactly what you already see here in this another busy plot for the CI chondrite. The only thing that I want you to understand here is we have a huge diversity of these different phyllosilicates. Every of these solid lines here is a different phyllosilicate. I even don't know all of the names. One of them is called lizardite. I always forget which one it is, which is just a fantastic name. And the phlogopite in purple here again as one of the relatively important condensates. But there is liquid water and also water ice stable. So can we actually force our bulk silicate Earth system to also have liquid water on the surface? Doing basically the exact same experiment as with the clay that I described just a moment ago. Just pour a bit more H&O on it and recalculate and see what happens. And what happens is exactly the same thing that we see here on the right-hand side, where we saturate more of where we form more of the phyllosilicates and then actually get some liquid water on the top. And if we do that even more, chuck even more water on it, we also get water ice to lower temperatures. So that is talking just about the crust-atmosphere interaction, but an atmosphere is much, much more than that. The atmosphere is actually consisting of a large column of gas. And as I said earlier, there's escape going on, all that fancy stuff. We don't include the fancy stuff yet. We just include a relatively simple setup for the atmosphere, where we just have a very simple pressure temperature profile. So the temperature of the atmosphere is just going down with increasing height with decreasing pressure. If some of you are a bit more known in the atmospheric structure of our own Earth, we have not just the decrease in temperature, but as soon as you get higher, we have also an isothermal region. We have some temperature increase where the temperature is actually going towards around roughly 0 degrees again, and towards the very, very top of the atmosphere, the temperatures actually reach many, many hundred or even thousand degrees Celsius. So there's a lot going on in there, but we are just looking at the lower part of the atmosphere where we have roughly some this pressure profile that we assumed here. And what we do in our model is to build our atmosphere from the bottom to the top. So we go from the bottom, solve for chemical equilibrium, just as described as before, take our gas phase, put the gas phase in the layer above. We have a slightly different pressure and temperature regime, recalculate our chemical equilibrium, and move up throughout the atmosphere. It will happen at some point that we actually have some thermally stable clouds or some thermally stable condensates itself at a given pressure temperature point. And then we completely take those out. We take all the elements of that that are condensing out. We take them, just let them stay at that height. It will be one cloud in our model, and only the gas phase is then taken towards the layer above. So with that, we already deplete our atmosphere in elements that are affected by the cloud formation. If we just have, for example, water clouds, the relative abundance of hydrogen and oxygen in the lower parts of the atmosphere will be much higher than in the high part of the atmosphere because we removed all of the H2O just in the meantime. So how does this look? Let's take a CI chondrite, as I've shown you before, for 350 Kelvin and 1 bar surface temperature. On this plot, the pressure, the atmosphere on the x-axis, the bottom of the atmosphere is on the right-hand side, the top of the atmosphere is on the left-hand side, and we start with a mixture of methane in the black dashed line, the gray line, nitrogen N2, and a lot of water actually dominating the atmosphere. And also some trace gases of carbon dioxide, ammonia, H2, H2S, and hydrochloric acid actually, no, actually not hydrochloric acid, but HCl, hydrogen chloride, and carbon monoxide at very much lower lower abundances. And as we go through our atmosphere, you can see here now the effect of removing of clouds. We see that the H2O abundance drops from being the most dominant gas species to be number 1, 2, 3, 4, 5, actually number 5 in abundance. Whereas some other molecules like H2S, this turquoise color, stays roughly the same until a certain point in the atmosphere, and then suddenly there is the removal of H2S, and that is because of a cloud that forms there. So what are these clouds that are actually forming? And are they depending on what the surface composition is? And the first question of that I can answer relatively easily. The clouds are shown here, which are water clouds in this model. In blue, there's graphite, so just pure carbon that is condensing in the atmosphere. And then the other two cloud layers are ammonium chloride and ammonium hydrosulfate. And if I just go back one slide, we see the H2S is just dropping exactly at the point where the ammonium hydrosulfate is forming. So that's a direct point where we can actually really see the effect there. We see also that the abundance is different of these various different clouds. So the water clouds, the carbon clouds are really, really high in number. So there's a lot of them, whereas the ammonium chloride, at least in this model, is not that abundant. It's not that much of it that we have. But this is just looking at it for one surface temperature, one surface pressure. In order to really understand what's going on and to not just model each and every individual planet on its own, we have to take a bit of a different approach to this, and just looking at everything on a plot by plot basis probably wouldn't work. So let's just put many of these models into one plot. And that's right now without any clouds here shown, just to introduce the plotting scheme basically, is that we have the different surface temperatures here. on the x-axis and the atmosphere going towards the y-axis here. So from 300 Kelvin to 1000 Kelvin is our surface, all at 1 bar at the surface, and every atmospheric model is 1 column here. So if we start, for example, with 500 Kelvin down here, we go up in our atmosphere, reach 400 Kelvin at 10 to the minus a half bar, then 300 Kelvin at just below 0.1 bar, and then reach 200 Kelvin higher up in the atmosphere at 10 millibar. So let's now just populate this plot by all clouds that are relatively high in abundance, and that we can therefore we get this beautiful colored plot, which is already telling us one big thing, one crucial thing. And the crucial thing here is that you should note that we do not have any clouds that are abundant in this whole middle temperature regime. So 400 to 600 Kelvin roughly in actual gas temperature. There are no clouds. There's no cloud really abundant there. And that's actually one of the results that I found that are happening for almost all element abundance. Actually, there's just one condensate that is really populating this this regime, and that's going to be on in a few. We're going to be the point of discussion in a few moments. But what are these clouds now? So we have this high temperature clouds and the low temperature clouds. The high temperature clouds are actually made out of very interesting molecules like sodium chloride, potassium chloride, or iron sulfur. Sodium chloride, actually, we all know it as salt. So just salt clouds. There are salt clouds basically hanging in these atmospheres, whereas iron sulfur is then in the slightly higher atmospheres occasionally becoming FeS2, which is also known as fool's gold. So there's pyrite, the geological term for fool's gold, hanging in some of these atmospheres. Whereas in the lower part of the atmosphere, we have, as I mentioned before, graphite, we have ammonium chloride, and what we haven't seen before, just above 400 Kelvin in all of these models, we have actually S2 in orange here. The orange region, we have sulfur condensing out, so sulfur cloud. So if we would assume that we just see this planet here with this total element abundance, and we would find, oh, this planet has sulfur clouds, we could say, oh yes, we have to have surface temperatures of roughly 400 to 600 Kelvin according to this model. If we compare this now to the bulk silicate Earth model, the image stays basically the same thing. We have the high temperature condensates. There's actually one additional one, which is Al2O3 corundum, aluminum oxide. And at the lower temperatures, there are just a bit less condensates, but still there's a big separation, except for graphite. Graphite is actually very special and very cool and interesting because it breaches this gap of high temperature and low temperature clouds. Another thing that we see is when we only focus on water, because as every time when one discusses rocky exoplanets, there comes the question, is there liquid water? Or is there water ice, or is it bone dry? And what we see on this plot here is just the extent of the water cloud layer, basically. So we have the water layer high up for the bulk silicate Earth, which is just water ice, just thin water ice. You can basically imagine like on Mars, where we, even nowadays, we occasionally have water ice clouds, although the surface is bone dry. And then for the CI chondrite, actually the liquid water, the dark blue color here, is actually touching the ground, which means it actually has liquid water at the surface. So with that, we basically have the three regimes that we can have. We have planets which just have a bit of water, not enough to actually condense water at any point, but still there are a few water molecules high up in the atmosphere, which are potentially observable. Or we have just enough water to form water clouds somewhere in the atmosphere, but not at the surface. So even detecting water clouds would not be enough to say this planet has liquid water at the surface. And then the ideal case, basically what we have on Earth, that we have water at the surface. There's quite a lot of water in the near surface atmosphere, and then we have clouds, basically water clouds, basically everywhere in the troposphere. So ranging from the ground, fog, to 10 kilometers up in our atmosphere, basically thunderstorm clouds, cumulonimbus clouds. They span basically the entirety of the troposphere, of the lower part of the atmosphere. And then with that there comes another question. How even deep is our atmosphere? How much pressure do we have at the surface? It's another unknown of observations of rocky exoplanets. We can, if we just go back here, we can say, oh yeah, we have some water molecules up in the atmosphere. We could potentially say, yes, there is a water cloud. And if we have our surface actually up here at lower temperature, lower pressures, something like Mars, quite low in pressure, we would have water clouds touching the ground, so liquid water stable. We could have something like Earth, where it's just a bit deeper in the atmosphere, still stable. Or we have something like Venus. There are some water droplets probably around in the clouds of Venus, but the surface is just so deep that we will never have any liquid water stable because it's just getting too hot. And that's another big question for exoplanets that we detect, because we don't know how deep the atmospheres are. And that's basically what I want to show you here on this plot, where we have different surface pressures. So the black line here at the bottom is different surface conditions at different pressures. And the blue line, the blue clouds here, are basically our water clouds again. So this model is just created in a way that we have water clouds everywhere at every of these surfaces. And one can imagine to observe this planet at the high parts of the atmosphere. And in this model, if we would observe exactly this planet at these abundances with that pressure and temperature in the high parts of the atmosphere, and we find some graphite clouds and ammonium hydrosulfate, this olive colors here, we would have a relatively shallow atmosphere. Whereas when we find some H2S clouds, which will, with the water, will potentially react to H2SO4, which is the cloud condensate that we have on Venus, we actually have to have a very thick atmosphere, a deep atmosphere. So observing something like H2S as a cloud condensate could tell us, yes, this planet has to have a deep atmosphere, so a high surface pressure, which is really cool. The last part that I want to talk about is atmospheric characterization. So whether or not we are capable of actually telling the atmospheric type of a planet, which would be ideal to just look at some molecules in the atmosphere and say, we found A, B, and C, so this is this atmospheric type, and therefore the surface is like that. Will not be that easy, but we are working towards it. And working towards it with cloud condensates is one part, and the other part is with the different atmospheric types. And there, I just want to focus on a few elements: carbon, hydrogen, nitrogen, and oxygen. And actually, if you have those 4 elements, the most stable molecules would be methane, nitrogen, water, and carbon dioxide. And every other molecule that you can imagine going into that cloud of these 4 molecules will react somehow with some of these to some other, and that's actually a very useful reaction that provides energy, and providing energy by giving up heat is basically telling you it's a favorable reaction, so it will occur at some point. For example, if we have H2 that we add to the cloud of molecules, will react with the carbon dioxide to methane and water, and that is favorable. For example, oxygen will react with methane to carbon dioxide, and then the leftover hydrogens will basically form H2O. And with that, we can actually form one atmospheric type, which is we have the coexistence of water, carbon dioxide, and methane. Oops, sorry, that was moving in a wrong position. I just clicked something that I shouldn't have clicked. And if we put enough hydrogen, for example, into this this cloud, we basically deplete all the carbon dioxide. So it reacts with it and reacts until there's no carbon dioxide left anymore. And then we accumulate our H2, leaving us with a water, methane, and H2 atmosphere, type A. And we can do the same thing with oxygen. We are leaving with a water, carbon dioxide, and oxygen atmosphere. And that is then our type B atmosphere. Or in a bit more graphical terms, where we have the carbon content on the x-axis, so how much carbon there is. The more you go to the right, the more carbon, towards oxygen and hydrogen content, pure hydrogen on the bottom, pure oxygen at the top. And there we have these three different atmospheric types forming lovely separated triangles. So type C, everything in this triangle, type B, everything above, type A, everything below. If we're looking at our solar system bodies, we have Titan down here in the bottom right corner, methane world, basically entire atmospheres, methane, Mars, Venus, carbon dioxide atmosphere, oxygen, and O2 atmosphere. Yes, we're completely ignoring N2 at this point, and if we do so, Earth basically has an O2 atmosphere, and Jupiter is very basically only H2. So the question comes into play: what happens if we put our own models into these? So each and every atmospheric model has the atmospheric composition at every layer, and let's just put them on here in this graph and see where they land. For the bulk silicate Earth, we end up with this wonderful group of lines. Every time when there's a number given, that's the bottom of the atmosphere, the surface temperature of the atmosphere. Let's just follow this 600 Kelvin surface temperature line. And as soon as we go throughout this atmosphere, we move in this parameter space, but we do not leave the atmospheric type region that we formed in. So as soon as we know the surface composition, the surface gas composition, we know we will stay in this atmospheric type. We have some movement by condensation. Movement to the left on these lines is just graphite condensation, so basically just taking out graphite. And as soon as we move a bit towards the top or the bottom here, we actually have water condensation. Those are basically the two that actually drive this, this graph here. But what still remains, we do not change our atmospheric type. Also for the CIA chondrite, doesn't happen. And for all of the other element abundances that I looked into, it does not happen, which is really cool, because if it is possible to actually get the atmospheric type of that planet higher up in the atmosphere, that can constrain our atmosphere towards everything that's below. So if we know, for example, that our atmosphere ended up down here somewhere, let's say where this 300 actually is written, we know that just this parameter space up above here is the possible surface condition. So we can constrain this. If we then can also get some cloud condensates, we might actually be even further able to constrain it to some more elemental abundances. And with that, we can step by step basically go towards actual characterization of the surfaces, characterization of understanding what are the surface conditions. And with that, I will want to leave you with my take-home messages. So my talk in brief, we have an atmospheric model going from the crust towards higher parts of the atmosphere. There's some cloud condensation depleting the atmosphere. And then we have some leftover atmospheric element abundances, which are forming the upper atmosphere, which can be observed. And at the very bottom of the surface, we need to hydrate all of the rocks before we actually get liquid water stable. As I said, we have cloud formation depleting the atmosphere above in all affected elements, and that can already constrain us a bit the surface composition. And we have atmospheric types, which can actually allow us to look at different parts of the atmosphere and say, we have that part of that atmospheric type, and therefore the same atmospheric type is present at the surface. Thank you very much for listening, and any questions that you have, as Pete said, I will hang out for a bit longer today, so there will be time to chat, and I'm really looking for your questions. Thank you.
Thank you very much, Oliver. That was an excellent talk, and quite a different take on the sort of talks we normally get with this sort of chemical composition of atmospheres. It's a very fascinating take on it. We've got a couple of questions actually have come in. The first one is from Keith and Angela Nicholson of Caithness Astronomy Group, and it basically asks, has the GS Chem model been applied to the solar system? You know, boiled sort of planets like Venus and Titan, to test its validity of the, you know, the species, you know, and the species model, to validate the species model conclusion. You know, how did you sort of validate it? I think.
Yeah, that is an excellent question, and that is one thing that we did, at least for some of the planets. We did one model that we did is basically trying to replicate Earth as an atmosphere, to basically have the same cloud heights where we observe water clouds on Earth, and we basically have to completely tweak the element abundances, which is possible, and then we actually get the exact result to get the water clouds at the correct cloud layer. We do not get some parts of the methane composition in the gas phase, for example, because that is produced by biology, and there's no biology in this model, so it shouldn't be there. And actually, yes, we don't get it as expected. For Venus, one has to tweak a bit the element abundances again to work towards the result. And yes, that is possible. We do get H2SO4 clouds in our model. Talking about Titan gets a bit trickier because the temperatures are really, really cold, and the colder you get, it just is harder to calculate the chemical equilibrium because just the temperature is just too cold. But for simple atmospheric compositions, yes, we do get at those temperatures one can get basically lakes of methane if one goes cold enough. But so cold is really is difficult for computation times, for computational reasons. But yes, overall, it is possible, and we've done it for some of them.
Great. No, that's a good answer. It's now, you mentioned that graphite spans between two of the phases in one of the graphs. What feature of graphite causes it to do that?
That is an excellent question. I have no answer for that, because that's one thing that I also would love to look into it. It's just that graphite is just a very, very, very stable form of carbon. And carbon is basically present in every atmosphere. And it has to condense somehow if there's just too much of it. And for some very hot atmospheres, we also get some magnesium carbonates, or so MgCO3, for example, as a condensate. But carbon is actually just pure carbon is just super interesting because it can be stable already at these high temperatures, but also at low temperatures, which is just makes carbon graphite so special. So far, we are not really sure whether these actually will form in a kinetical actual model, where we actually take the actual cloud condensation and cloud growth processes into account. But that's one of the things that we really want to do in the future, to really get these graphite clouds into more sophisticated models, to really investigate whether or not they form and I think they will form if the circumstances are right, and that is remains to be seen.
Yeah, rather interestingly, I was going to say, well, what's your next bit of work here? And obviously, that you've answered that question in answering this other question. So
Actually, just half,
well done, mate.
because more of my work will actually be on this upper part of the atmosphere. So not just the lower part of the atmosphere, but basically combining the lower part of the atmosphere to upper part atmosphere models, where we have the atmospheric escape, so that one has a full model from the surface to the atmospheric escape. And that is also one of the other additional really interesting steps to look into, and habitability. I would love to have more discussions about habitability on other planets. It's always fascinating what life can be out there.
It's a fascinating enigma, isn't it?
Yes, great.
Got a really good question here from Pete, actually. His question is, or comment firstly, is it appears that, like the solar system, there seems to be no exoplanets in the size range between Earth and Mars size, and then it goes sort of straight out to the gas giants. And Pete's question is basically, what's the reason for that?
Well, actually, there's basically a gap, not really between around Earth sizes, but there's a gap at like a bit larger than Earth. So when we go to like 3 Earth masses or so, then it becomes a bit less densely populated in the big scheme of exoplanets. So we have a huge variety of different rocky bodies that grow a bit larger, a bit smaller, basically no real difference. But then at some point they grow so large that they can actually get into get the hydrogen envelope, basically during the planet formation. And as soon as that kicks in, they just eat up everything that's in their surrounding, and then they end up as large planets, as Jupiters. But if they just happen to reach this critical mass of accreting the hydrogen bit too late, so that there's not that much hydrogen left anymore, or if the host star is irradiating the planet too much that actually strips away the atmosphere, we are left with a bare rock again, and that will then be a relatively massive core of a let's say former Neptune-like planet, whereas that will then be slightly different in their formation history than a rocky planet like Earth. So there are multiple different variations how you can end up with a given mass and given radius, but that is part of modeling approaches of many different colleagues, actually. Some also here in my group in Graz that you previously used to be in St. Andrews, which is a very interesting question to tackle. Yes.
Yeah. You mentioned that one of the planets was molten in the early part of your talk. How did you work that one out? Is it just its proximity to the planet, the sun, and just a guess that it had a huge amount of solar radiation, or
exactly,
or was it just the chemicals it gave off, basically?
Well, basically, you answered your question. It's just if your planet is getting closer to the host star. If we look at our solar system, we have Earth, lovely temperatures. But if we go to Mercury, it's already pretty hot because we have just so much incoming radiation. But these planets, these molten super Earths, they are not just orbiting at like Mercury orbits, but rather they are orbiting their host star in just a couple of days. So they're so close to their host star that they are also tidally locked. So basically the same thing what our moon is doing with us, just facing the same side to the host star, or the moon to Earth. The same side is always faced to the larger body of mass. And then there's just radiation, just pure radiation all of the time, every day. And that's just, if you're so close to the host star, will just lead to temperatures exceeding 2000, 3000 Kelvin. And then at that temperatures, you just melt every rock basically and just have a magma ocean.
Yeah. Okay. Hey, well, that's great. Thank you very much for answering those questions, Oliver, and thank you very much as well for an excellent talk. I think you know, we tend to get a lot of talks in the astrophysics sort of area, and these talks on, you know, chemical composition of planets and that sort of things are, you know, it's a very fascinating subject, and obviously one that's still having a lot of research done on it. So thank you very much for coming along and giving us a talk tonight. We noted actually you like whiskey, and so as a means of thanking you for the talk, we were thinking of sending you a whiskey tumbler. So as a means of thanking you, so
that is wonderful.
You've got something to put your whiskey in now, mate.
that is wonderful. Thank you very much.
Not at all, and well, thank you. It's a superb talk and detailed, and yeah, quite a complicated subject matter, but well delivered. Thank you very much.
I'd like to second that. It was absolutely fantastic talk. Well done, Oliver. Brilliant.
Thank you.
We will promise now to get you up into Murray sometime to do another one. Okay.
7 stilts. I have to visit all of them.
Yeah.
At least.
So, well, that's just in Dufton, you know. So there's a lot more. Like
I know.
Yep. There we go. But
yeah.
no, that's. We will get you up, as I say. We're hoping to get back to live meetings again from April onwards. So maybe next year or the year after, whenever you're free, we'll contact you again and get you up in person.
I will be back to Scotland. I promise.
Yeah, good on you. Thanks again. Thank you. Thank you very, very much. Okay, everyone. As I say, we'll go over to the break now. But just before we do, you see a little raise hand button at the bottom there. Who's actually looking forward to getting back to physical meetings? If you are, click your raise hand button. Let's have a look at your. Come on. That's 5, 6. Oh, someone ran back down. 7, 8. Yep, it's looking good. Okay, so it looks like quite a few of you are looking to getting back to physical, you know, sort of say back to physical meetings. I'm certainly know I am. Okay. Yeah, will do. Okay. Right. So we'll say we'll head on to the break now for 10 minutes. So that will take us up to 1:45. So the chat's back on. If you are going to chat with people, just remember to click in the drop-down box and put it to everybody. Otherwise, it might only just come through to us. So we'll head over to the break now for 10 minutes, and we'll have a little dram maybe, and we'll see you back at 1:45. Okay, everyone. See you in a bit. Okay, welcome back, everybody, to the second half of this Sigma meeting. If Stuart is ready, we will go over to him now for the space news.
Okay. Okay, welcome, everybody.
Okay, Stuart, it's you.
Space News for February 2022. There's a few topics I've chosen that cover various aspects of what's happened over the last 2 months, actually. Some of you may have seen it on some bits on the news or may have updated information, but I've tried to get the best information I can at the time that I wrote it down. So we've got tardigrades and Israeli lander, China's new space station, Perseverance rover chokes on Mars pebbles, SpaceX Starship launch and catch tower, the Easter Sentinel-1B anomaly in orbit, nuclear propulsion for satellites, and Artemis going back to the moon. I think, I don't know if you remember this, it's about 2 years ago, we came up with the tardigrades. They're about 1 meter long, but vary from 0.05 of a millimeter, did I say meter, they're millimeter, 0.05 of a millimeter to up to 1.2 millimeters, but on average, they're about a millimeter in length. They're effectively known as a water bear or a moss piglet. In 2019, the Israeli Beresheet mission crashed while attempting to land on the moon on board with microscopic tardigrades, and concerns were raised about contamination. Now, at the time, they hadn't declared what was on board until it crashed, and it was afterwards that they found out that these tardigrades were on board. It is known that tardigrades can survive temperatures close to absolute zero, withstand heat beyond the boiling point of water, and shrug off the vacuum of space and doses of radiation that will be lethal to humans. However, researchers at Queen Mary University of London wanted to know if they would survive the impact of crashing on the moon. They subjected the tardigrades to impact at the speed of a bullet. They wanted to conduct their experiment ethically, and I find this quite odd. So after feeding about 20 tardigrades moss and mineral water, they put them into hibernation, a so-called ton state in which their metabolism decreases to 0.01% of the normal activity by freezing them for 48 hours. I'm not sure why they needed to feed them first, but they then placed 2 to 4 at a time in a hollow nylon bullet and fired them at increasing speeds using a 2-stage light gas gun, a tool in physics experiments that can achieve muzzle velocities far higher than any conventional gun. Bullets were fired into a sand target several meters away, and it was found that the creatures could survive impacts up to about 900 meters per second, or about 3,000 kilometers per hour, and momentary shock pressures up to a limit of 1.14 gigapascals. Above those speeds, they just turn to mush. The findings are reported in the astrobiology news if you want to get more information on them. But some things actually came out of their research. So although the lander is thought to have crashed at a few hundred meters per second, the shock pressure of its metal frame generated hitting the surface would have been well above 1.14 gigapascals. And researchers confirmed the tardigrades would not have survived. It was unlikely that they would have survived effectively. But it also placed new limits on a theory known as panspermia, which suggests some forms of life could move between worlds as stowaways on meteorites kicked up after an asteroid strikes a planet or moon. Eventually, the meteorite would impact another planet along with its living cargo. Now, someone we've had speaking to us before, Charles Cockle, responded to this. He wasn't involved in the research, but responded to this, saying that he didn't think that was possible for that to happen. However, the Queen Mary University of London students or researchers said it's hard perhaps for it to happen, but it's not impossible, because meteorite impacts on Earth typically arrive at speeds of more than 11 kilometers per second. On Mars, they collide at least 8 kilometers per second. They're well above the threshold for tardigrades to survive. However, some parts of a meteorite impacting Earth or Mars could experience lower shock pressures that a tardigrade could live through. So they believe it is possible that these tardigrades or some similar microscopic creature could survive transfer from one planet to a moon or planet to another planet. They also raise the issue of moons that generate water and satellites passing through these water vapor that comes from the center of a moon could actually pick up any living item, but they'd have to be traveling at a slower speed. And we've got nothing that actually does that at the moment. The sort of speeds we're talking about, which the tardigrade would survive. So I think, although they've effectively proved that the tardigrades wouldn't have survived the impact on the moon, there's further study to see how they could be transferred from planet to moon or planet to another planet. So that's continuing. Now, China's new space station. China is preparing and carrying out tests on its new Tiangong space station ahead of upcoming module launches. It has successfully grasped and maneuvered a cargo spacecraft in a crucial test. The 33-foot long robotic arm on the Tianhe module of the space station took hold of the Tianghu 2 supply ship and moved it around 20 degrees before returning it to the forward port on Tianhe's docking hub. And as you see what it's doing there. The test is seen as vital to the China National Space Administration's plan to complete construction of its space station later this year. The next space station modules, named Mengtian and Wentian, are scheduled to launch on separate Long March 5E rockets in the coming months and dock with the orbit in Tianhe. The robotic arm will then grasp the modules, each with a mass of more than 44,100 pounds, and maneuver them from the forward port to radial ports. And that's an illustration of the final completed space station. And it'll have three effective modules on it when it's finished. So in addition to the Tianhe 2, which is up there and supplied the last crew mission, there'll be further 2 modules which will be launched later this year and will be attached to the missing arms, which you can see on, if I go back there, on there, the missing arms on the end of the 2 shades. There. Tianghu 2, launched in May 2021, was the first visitor to the newly launched Tianhe module. So it started off as a single module. It carried the propellant for Tianhe and delivered supplies, equipment, and experiments ahead of the Shenzhou 12, which was a crewed mission, which ran from June to September. It has remained docked to Tianhe to be used in tests for moving the future space models, and the cargo spacecraft will be deorbited and burn up on re-entry once after the tests are complete, carrying with it waste material from Tianhe. There will be a further 2 more launches of a supply rocket and module, and 2 more crew modules, and the final crew module will be there when the 2 new extensions of the space station will be sent out. Perseverance rover chokes on Mars pebbles. They had a problem with the, if you remember early on, they had a problem with the Perseverance when it couldn't get its first samples because the soil or the ground was too soft. It was crumbly. It wouldn't pick it up. They have now. This is the 6th attempt. They then had 5 attempts which were successful. This is the 6th attempt, and they found out they picked up the sample, but when they transferred it to the inner tube, it wouldn't close down properly. So they had to try and release it. And that shows it fully blocked in the tube. They then rotated it and used the drill to turn it down and point it down to the ground, rotated it, and you can just see the bits falling out there as they are doing. However, that didn't actually clear everything out of the tube. So what they had to do, they found some rock which they could rocket backwards and forwards to get the last of the pebbles out, which was choking the system. And it's now back to normal and continuing with its sampling. So hopefully that'll continue now and continue to get enough of the samples, which won't be returned to Earth until 2031. in a NASA stroke ESA mission to pick up the samples. SpaceX Starship launch and catch tower. In order to launch the Starship, SpaceX have produced this. Elon Musk took a video of his catch tower on Twitter and put it out on YouTube, and this is what it looks like. I'll show it on there. It was better than the image, but I actually use this to see the size of it. It's quite a large facility with an arm to catch the top of the booster rocket and also the spaceship. The ultimate goals of the tower include stacking Starship's 2 reusable elements, that's the first stage booster, the Super Heavy, and the upper stage Starship, serving as a launch pad for the duo and also for catching returning Super Heavy boosters safely after flight. And the tower is under construction while SpaceX prepares to launch its first Starship orbital test flight, which will involve the prototype spacecraft SN20 and Super Heavy Booster 4. SN20 has successfully performed multiple static fire tests to prepare for the mission, igniting its Raptor engines briefly while the vehicle stayed anchored to the ground. The ESA Sentinel-1B has an anomaly in orbit, which continues. The Sentinel-1B radar satellite, part of the European Union's Copernicus Earth observation program, hasn't beamed home any data since suffering an anomaly on the 23rd of December. And that's the Sentinel-1B. Sentinel-1B launched to a polar orbit in April 2016, 2 years after its twin Sentinel-1A. Together, the 2 satellites have been providing continuous high-resolution radar mapping of Earth for a variety of users. Each satellite is expected to gather data for at least 7 years, and each has enough fuel on board to operate for 12 years, according to a mission description. The Copernicus program is a project run by the European Union and the European Space Agency that builds and manages a fleet of Earth-observing satellites called the Sentinel, which these 2 are part of. 8 missions have been launched to date, providing data about changes occurring to the oceans, land, and atmosphere on Earth. And it also consists of 2 Sentinel-2 satellites, 2 Sentinel-3 spacecraft, Sentinel-5 precursor satellite, and Sentinel-6A, which lifted off in November 2020. And more are scheduled to launch in the coming years as well. It also incorporates data gathered by a number of contributing missions, which are operated by a variety of different organizations. And just a little bit more information on that, which is that Copernicus was created in 1998 when EU officials signed the Bovino Manifesto, a document proposing that Europe play a major role in handling worldwide environmental and climate issues in Bovino in Italy. And the program was originally known as Globe Monitoring for Environmental Security, as we intended to provide information that would help humanitarian aid, peacekeeping tasks, and border surveillance along with environmental concerns. And then in 2004, ESA agreed to create a space-based component of the GMS, and this is what this became. And it was renamed Copernicus in 2011 after the Renaissance era Polish astronomer Nicolaus Copernicus. Nuclear propulsions for satellites. The Defence Advanced Research Projects Agency, DARPA, has watched NASA work in nuclear propulsion systems for space exploration and believes that the technology can be applied to military satellites. To this aim, DARPA announced at the end of last year that it will invest nearly $30 million in a project called Demonstration Rocket for Agile Cislunar Operations, DRACO, which is a spacecraft powered by a nuclear thermal propulsion system. The DRACO demonstration is projected to launch in 2025, noting that it will use low enriched uranium. And that's a rendering of DARPA's demonstration rocket. The reason for it is that US satellites powered by chemical propellants have limited ability to maneuver, which make them easy targets and targets of anti-satellite missiles or weapons, and which is, I think, in the last year has proved that this is a possibility. Meanwhile, China's space maneuver warfare forces will include vehicles with nuclear thermal and electric propulsion capable of rapidly transferring between orbits to conduct offensive and defensive missions. And I think what they see here is that they'll be able to move in space a lot quicker with the nuclear thermal propulsion. And they're also thinking of connecting it, they're using it with the GPS and other satellites so that they can actually move out of the way, as well as quickly in terms of avoiding collisions, as well as improving the weapon capability of the systems. But they do say that on launch, they'll be using normal chemical propulsion and not anything that's radioactive. Artemis going back to the moon. April, May this year will see the launch of Artemis 1, an uncrewed test flight. It will be the maiden use of NASA's Space Launch System, which has been a long time coming, and it was due to be launched in March. But yesterday they came out with a notice saying that it won't move to its launch pad until March. So therefore the actual launch won't be until April or May. Artemis is a rocket that will send new Orion multi-purpose crew vehicle, MPCV, on a 236,000-mile long journey to the moon. If all goes to plan, it will be followed by a crewed mission, Artemis 2 in 2024, which will test everything out in an orbit. And Artemis 3, which will be a crewed mission, is planned to land on the lunar South Pole and spend a week there in 2025. As part of the Artemis mission, it's also introducing a gateway, which they plan to launch in 2024, which the Artemis 3 will probably link up to, and that will orbit the moon, and it'll be a space station, which will then be a base for other missions to actually land on the moon, go to the gateway before dropping down onto the moon. And this is an artist's impression of the Orion capsule. And this is the Space Launch System, which is quite some rocket. Now I've put this in here, which is a very complex one, but if I can get the laser pen, you see here the launch is going to take 26 to 47 days, the trip. I don't know why they said 2 dates, but two lengths, because I'm sure they would be more accurate than that. But the launch is here, jettison its rocket boosters, jettison launch abort system, and enters Earth orbit. It comes around here in Earth orbit, translunar injection burn, and then it's also carrying some CubeSats to deploy. So when the interim cryogenic propulsion stage separates, that'll go off and launch its CubeSats, while the ship itself will continue and do any correction there. Come round, it'll go retrograde, which means it'll go the opposite way around to what the sun is, the moon is rotating. And it'll come round here, do a flyby. I think I've got 14, 15. I think I've probably gone, there we go, 16. Return power, flyby, and then it'll return down there. So it's quite an interesting first trip for that, and then that will be followed by Artemis 2 and hopefully Gateway in 2024, and then a crewed mission to land on the moon 2025. Okay, I'm sure there'll be more about this later, especially once it gets close to the launch on what it's doing. And that's all. Thank you.
Thank you, Stuart. That's brilliant. Again, it's good to see that we are actually returning to the moon at last.
Yeah, there are some people saying, well, we shouldn't be doing it. I didn't put that in.
Yeah, I know. Well, there always will be, won't there? I bet they believe in the flat Earth as well. No, I was just wondering when it will actually gain the interest again, you know, like Apollo did, you know, whether people start looking up again and looking into space a bit more. And
yeah,
you know?
I think it's more on the doorstep, isn't it? People
It's going to be more, you know, sort of more accessible with the internet and that as well. So yeah, it'd be interesting. Something to watch for the future.
Yeah.
Okay. Thanks, Stuart. Okay, Mick.
Okay.
I can see you're ready. I don't think there's any questions. Is there, Rich? None at all. I've seen them come in. Nope. Okay. Right then, Mick, over to you for the Morning Sky at Night. Okay, we've got that.
Oops.
Mick, you made my mistake. You're muted, mate. You're still muted. Okay, it looks as though we got a little technical hitch going on. Are you okay there, Mick? Does that help?
Cheers, Pete. Can you hear
We've
me
got you.
I've completely lost my Zoom controls. I can see you, but I can't see any of my Zoom controls. So I don't know where
Right.
they've gone.
Over to
Okay. Right. Good evening, all. Welcome to the February edition of Sigma's Murray Sky at Night. As usual, I'll start with the moon and the planets. And start with the inner planet. Mercury is a dim morning object this month, not well placed at all, but it's best seen just before mid-month. Venus is a bright morning planet, rising over 2 hours before sunrise, and that's going to be near Mars at the end of February. Mars is a brightening morning object. Jupiter can be seen, as you can see here, just after sunset, but that's soon going to be too near the sun to be visible. Saturn reached superior conjunction today, so it's basically on the far side of the sun, so that won't reappear until mid-month, when it will appear early in the morning sky. So Uranus, the next planet out, if I go forward to the 7th, it's going to be 1.2 degrees north of the moon. Neptune is in Aquarius at a magnitude of 7.9. So some photo opportunities for anybody who, I'll stick some constellation lines up so you can see where everything is. Moving on to the 9th, the moon is going to be between Aldebaran and M45, the Pleiades. Let's get some information here. There you go. And if I zoom out, carrying on to the 13th, the moon will be just 2.6 degrees south of Pollux, one of the twins in Gemini. And continuing on, I'll get a bit later at night. 16th, it's going to be just to the north of Regulus in Leo. Also this month, worth a mention, is Comet 2019 L3 Atlas. Now it's going to be pretty tricky to find. you're going to need, it's a faint magnitude of plus 12, but it's going to be traveling through Gemini. If I get the, let's find it. Oh, come on. Oh, there's my zoom controls just appeared on that screen. Bit late. So if I go back to tonight, it's going to be traveling through the month. That's not went onto it, has it? What's happened? There we go. So it's going to be pretty faint. You're going to need a 6-inch telescope or more to be able to catch it. But it could be a good photo opportunity for anybody interested. It's going to be traveling down this kind of direction across the legs of, if I can get it to stay in the center of the screen, through the month it's going to be, and the moon is going to get in the way on the 12th. But it'll be traveling across the legs of Castor as the month goes on. So that's a comet for you to go and hunt down for all of those into the imaging. That's the moon and the planets. So let's go and have a wee look at some deep space stuff. Back to, I'll go to tonight at 20. I've gone to tonight because it's closest to the new moon, which was on the 1st. Right, to go to the south. I must have clicked something wrong here. There we go. Right. Okay, so I make no apologies this month. A few of these targets we're going to look at might be quite challenging to find, let alone see, but I'm sure we all have a challenge. And of course, us living this far north, we only get half of the year, that's weather permitting as well, to be in with a chance of finding these objects. So I thought I'd pick some of these out. What we're going to look at is some late winter planetary nebula. So what are planetary nebula? Well, they're a type of emission nebula that consists of an expanding glowing shell of ionized gas, which has been ejected from red giant stars late in their lives. The term planetary nebula is a misnomer because they're completely unrelated to planets. The term originates from the planet-like round shape of these nebula, which were observed by astronomers through early telescopes many moons ago. All planetary nebula form at the end of the life of a star of intermediate mass, which is between 1 and 8 solar masses, and it's expected that the Sun is going to form a planetary nebula at the end of its life cycle. So we're going to start the tour with NGC 1535, Cleopatra's Eye. Now this lives in the southern constellation of Eridanus, so we don't get to see this very often at all, and as you can see it's pretty low down on the horizon. It starts from just below the foot of Orion and it goes up to almost in line with Orion's belt before it snakes right down. I'll show you the, if I lift this up and move the ground out the way, you can see it's a massive constellation that we never get to see, but there you go. So, as I say, Eridanus, a long winding celestial river, and with it being a southern constellation, it means it's flowed under the radar of many UK observers up till this point of the year. So NGC 1535 peaks at around 15 degrees elevation, not particularly high, and it culminates in peaks in altitude due south in the early evening around about 6:30. So you want to get your observing or imaging gear out ready to go as soon as darkness falls. So to find it, there's quite a bright star here. If we aim for this one, Zorak, I'll just zoom into this. And looking across towards this star here in Eridanus, 53 Eridanus, round about halfway-ish is where we'll find it. There we go. Okay, Cleopatra's Eye Nebula. Excuse me. Deep images reveal it as an exquisite object, and it's certainly a prime target for remote imaging. It's one of the finest planetary nebulae in the entire sky when viewed from more favourable southern locations. Nevertheless, from mid to northern latitudes, it's bright enough at a magnitude of 9.6, and it exhibits such a high surface brightness it can be picked up as starlight through a 3-inch telescope. A 6-inch telescope, though, at high power can resolve it, while larger telescopes, preferably adding an O3 filter and imaging, can also show the nebula's vivid aquamarine coloration and reveal a faint outer halo encircling a brighter inner region. Excuse me. So that's the Cleopatra's nebula. Next, we'll move on to another southern constellation, even lower down on the horizon, Puppis. So to find that, we head across to Sirius, the brightest star in the sky, which you should be able to find. It takes a little bit later in the evening to come up, but in fact, I'm going to have to move to about 11 o'clock. Let's go to 11 o'clock. And of course, Sirius is in Canis Major, and just coming up over the horizon here is Puppis. What I can do again, just to show you what that constellation looks like, 'cause it's not one we often get to see, or if ever. There it is here. So it's just poking the northern half of it above the horizon. And what we're going to look for here is NGC 2440. So Puppis is known as the stern or the poop of the ship Argo Navis. NGC 2440 is a small though bright planetary nebula. As you can see, it's going to be a bit tricky to find. On mid-February nights, it culminates at 10 p.m. GMT with an altitude of only around 7 degrees. So it's going to be in amongst the murk. Unfortunately, so you're going to need a good view of the south to find this. So we head to Sirius, using a line from Sirius through this next star to its left, Iota Canis Major. And if we continue this line across the sky and then take an imaginary line directly north from this star in Puppis, where they intersect, you'll find 6 Puppis or Puppi. And according to my notes, it's located 2 degrees southwest of that, which is probably about, it depends how far I'm zoomed in, doesn't it? Oh, just missed it. So here we have beautiful butterfly. Well, it's known as a butterfly nebula. It shines at a relatively bright magnitude of 9.4, but it only spans 74 by 42 seconds. Despite its unfavourable altitude from the UK, a telescope of around 3 inches can track it down, but probably won't give sufficient magnification to show it as anything other than star-like. A 10 to 12 inch telescope at high power can show a featureless patch of light. But deep images shot through moderate to large aperture telescopes do show significant structure, especially when using narrowband H-alpha and oxygen-3 filters. It has a magnitude 14.3 central white dwarf remnant that's difficult to capture, though it's worth identifying it, maybe in deep images, as it's one of the hottest white dwarfs with a temperature of 219,000 degrees and a luminosity 1100 times that of the sun. So there's a little challenge, if you can find that. So next we're going to move up the sky into Monoceros, and what I'll do is I'll just pick the centre star because it's handy. So while the Rosette Nebula and Messier 50 are two of the most well-known targets in Monoceros, NGC 2346 we're going to look at now, though not a showpiece object, is its best planetary nebula. It's located at a peak elevation around 20 degrees from Murray at around about 10 p.m. But it may be a bit more challenging to observe as it's only magnitude 11.6. It's easy to pin down. It's just half a degree southwest of that star I've just clicked on. So it's around about here. It's going a bit. There we go. Right, NGC 2346, really attractive object. Deep imaging shows the likeness of butterfly, informally known as the Butterfly Nebula. It gets sufficiently high in the UK to make it a viable candidate for serious imaging. A 6-inch telescope might struggle to pick up NGC 2346 as in less than pristine observing conditions. An 8-inch telescope and more southerly claims will give a good view of the nebula's elongated form through a UHC filter at a power of at least 200 times, though a 12-inch telescope is probably going to be what you need for a similar view from Murray. So let's now head 25 degrees northwest into the mighty Orion. And what we're going to look for now is NGC 2022, a Cleopatra's Eye lookalike in Orion. It's the smallest planetary nebula yet on the tour, and it's not particularly bright either at a faint magnitude of 11.9. Despite these discouraging numbers, it is the brightest planetary nebula within Orion though, although competition isn't fierce. To find it, fairly straightforward yet again. If you go from Betelgeuse to Mysa, the next star across the top of Orion, it's round about here. Yeah. So that reaches its peak, a favourable 40 degrees or so around 8 o'clock at night. Imaging shows it to be a smaller version of our first target that we saw in Eridanus, although deep images show that this has 3 shells with an ultra-faint outer circle of nebulosity that accounts for around half of its diameter. It can be seen through a 6-inch telescope, though you'll probably need an 8 to a 10-inch telescope to show a small grey ring-shaped structure. Next, we're going to head up to Taurus, northern boundary with Perseus for our penultimate planetary nebula. So across to Taurus, we have Aldebaran, up to the Pleiades, get them centered, and so Perseus, here I said it's on the boundary. What I'll do is I'll put the boundary lines on so you can just quickly see if only these were in the sky, it'd be great, wouldn't it? So my notes say it lies 8 degrees northeast of Pleiades and 3.5 southeast of Attic. Attic is this star here. So it's round about here on the border. Okay, that's it. There we go. So this is the Crystal Ball Nebula. A large object spanning 2.3 by 2 minutes. Looks very attractive in images which show it has a very bright central star. It's a white dwarf remnant, shining at a magnitude of 9.4, making it an easy capture for a small telescope. Though the downside is that the distracting glow from this white dwarf could make the surrounding nebulosity quite hard to see. So try using averted vision through a 6 to 8 inch telescope on a fine moonless night. An O3 filter should suppress the brightness of the central star while pulling out the structure of the nebula. For a final target, we continue travelling northwards. There we go. And we're going to head straight across Perseus into Camelopardalis. Excuse me. Look for NGC 1501. Of course, Camelopardalis is a circumpolar constellation, meaning it never goes below the horizon from our hemisphere. You can see there's not a lot of bright stars up here at all, but among its faint stars we'll find NGC 1501, And to find that, let's just get to about that. Now, if we head up to this star here, and then across to this one, it's roughly halfway again. There we go. The Camel's Eye Nebula. Among its faint stars, we'll find that high surface brightness, nice ice blue colour that's brought out well in amateur images. This is high overhead, quite early on in the evening, so 6:30 p.m. Shines at around a magnitude 11.5 that makes up for this by offering a high surface brightness across its slightly elliptical shape. And that shape seen well in images. A 4-inch telescope on a dark, clear, moonless night should find it for you. Though a 10 to a 12-inch scope operating at high magnification is probably what you need to see some mottling that you can see here in the nebula structure. So that's tonight's tour. I have mentioned a few large telescopes this evening, but all isn't lost if you don't have a large telescope to hand. I certainly don't. With some planning, what you can do is use one or more of the available remote imaging platforms, including the likes of Telescope Live, iTelescope, Chilescope, or Slew. So as UK amateurs can sample some of these northern and also southern planetaries for yourselves. And that's all from me, Pete.
Wonderful, Mick. Thank you very much. It does say, I'm going to say that planetary nebulas, I love looking at planetary nebulas. It's one thing that got me back into astronomy. I lost interest a little bit when I was living down in Gloucestershire because light pollution killed any viewing I could do, but I got back up here to see the planetary nebulas is just wonderful. I say there are some, some of them are a bit challenging, but we all have a challenge, as you say. But there are some fantastic ones you can find nice and easily as well, but we'll do them on our observing evening. Okay, Mick, thank you very much.
Okay. Cheers.
Great stuff. Yeah, it's just, I'm going to say, planetary nebulas, it's just wonderful to see these death throes of the stars that are out there. And if you've never seen them, hunt one of the easier ones down and have a look. You soon know when you've seen them in your telescope because you've got all these bright stars all around, and then there's this fuzzy patch, small fuzzy patch in the middle, and you just know that's the death throw of that star you're seeing. Okay, just a little bit of club news to finish off with. Say we're still trying to find a suitable date to go down and see this astro kit that we've been donated. As I say, it's a little bit difficult at the minute. Obviously, weather is not going to help. And as I say, we're also looking at a site of where we can actually erect this dome that we've been given, and the telescopes as well. If any of our members out there have any ideas of where this could be, please let me know. I've got a little idea forming in my head. Sam, I think you're here tonight. I'll have a word with you later on about it in the gathering. Don't forget the telescopes for hire if you want to see some of these planetary nebulas that Mick was telling you about. We have the 6-inch Dobsonian that's available now. Don't forget, we're running out of time now. By the time we get to the end of March, the nights are going to just fling out into brightness, and we'll be losing any chance we've got to see anything. Once you get in the middle of April, it really is. Unless you're a night hawk and you stay up at 2 a.m. in the morning, you're going to be struggling. So we've got those for hire. If you want them, just let me or Rich know. There's a small charge of £5 just for, just covers any accidents that might happen or anything gets lost, and we can, sort of replace the items. As I said, please get them because I need one of them moved out of my observatory. It's just taking up space. Okay. So I know things are tight at the minute. If you're struggling, if anyone's struggling, we can always waive that £5 fee. Okay, so you haven't got to tell us why. Just say, look, I can't afford that this month. Can I just have the telescope? Let us know, and you can have it. Okay, so we've got that Dobsonian, and we've also got the Helios refractor as well, 3.5-inch refractor, free to the members to use for that small donation. Yeah, as I said earlier, we're looking at returning back to Lambride in April. With that practice meeting on the 12th of March, so put them dates in your diary. Now, I've had a request from Karen Cox to Celia and Kay, because the returning meeting we go back to is going to be Christopher Jennings. A lot of you will know Christopher from Sigma. He was was the youngest Sigma member a while back when I first joined, and he's still, I think, the youngest Sigma member to ever give a talk to Sigma. If you remember, you've done a tour, I think there was a Hitchhiker's Guide to the Galaxy, and he had his towel with him. You might remember that one. Can't remember how old he was, but he wasn't very old at all. He was still at school, I believe. But it will be him giving a talk in April. Okay, so, and Karen Cox asked me to remind, well, to let Celia and Kane know that that's Chris is doing the talk. And hopefully they'll come along and see him. And Karen says she will be there as well. So it'd be nice to see Karen again. She was the chairman for Sigma for many years and done a great job prior to Stan. And it'd be great to see Karen again, actually. It will be. Obviously, if we go back to live meetings, the Zoom, we might have to do a bit of a hybrid at the moment. It all depends if speakers are happy to travel up and go into a hall. We might have to do a hybrid sort of situation where we've got some on Zoom and some in the hall. But we are, once we go back to the hall, we want to stay at the hall. This is the reason we left it a little bit later than some. But we are hoping that we can record the live meetings and then put them onto YouTube later. For those of you who are a little bit out of the area, or those of you who can't make the meeting, or those of you, to say that let's say can't sort of make the meeting because of work sort of, commitments, or if you're a little bit worried about coming to a meeting just of yet, with everything else still going on, we hope we can do this for you and you can catch up on YouTube later on. If there's any members out there or budding cameramen or camera women who want to take on this or give us a hand to do it and know how we can do it, please let us know. You can come along and we can set up and we can do it, do it at the practice meeting in March if you want. We are looking into what cameras we can use in that, but say our knowledge is a little bit sparse on that, how we're going to do that. Okay. Let's say YouTube, all the recordings are on YouTube. This one will go on in a couple of days' time. I will send the link out to members if you want to watch it again. If you missed anything or want to catch up, you can, well, you can do that. And all the other ones, they run 6 months behind. They all go live 6 months behind. Okay, so in 6 months' time, this one will be out to the public if we're allowed to do it. Oliver, I'm sure you'll let me know. Outreach program, we have restarted the outreach program. I don't think there's any reason why we can't do it in person. So if you've got any clubs, societies that you want a talk, then a simple basic astronomical talk to any clubs, Cubs, Scouts, whoever, just let us know and we'll try and organize what we can for you to do that. Okay. Observing nights, we had a great observing night on the Saturday after last month's meeting. It was just great. It was just great to get together again. It's been so long since we've been able to do this. Karen was there, Karen Fullerton, and she loved the night. It's the first time I think she'd really been out and been shown the night sky. Myself, Stuart, Tim, Richard, Celia was there as well. So it was 6 of us there, and it was great. It's just a couple of hours. That's all it needed. We started nice and early. But it was just brilliant. So I've missed it so much, and I think everyone else had. And so our time is running short now with moonlight and weather, and the night's drawing out for us to do this. So if we get another chance, please come along. We'll, say we've got to get back to being together again. Don't forget to invite a friend if you've got any friends that are interested in astronomy or have got a slight inkling of, oh, what's that all about then? Just let them know about us. Show them over to the website if you want to, or just give them my email or Mick's email and we can send them out the membership information. Okay. And let's say if there's any, the Zoom gathering, I think the link has just gone up in the chat now. So once I finish my bit of waffling here, just click that link and it should take you straight over to the waiting room for the gathering. Everyone's invited, all our associated club members, any guests, come along, have a chat, have a natter, have a whiskey. I'm sure Oliver will. I'll have a whiskey with you as well, Oliver. I've got some here. So we're gonna have a bit of a chat and a bit of a laugh. Okay. And if you've got anything for me, anything from anything you think we could do better, or anything you think, I'd like to see something like a bit more something else, let me know. As I say, I've always said it's your club, not my club, not the committee's club. It's your club, and we run it for the best we can do for you. Okay. Now, the next meeting is on the 4th of March, and it's meant to be Rose Rott, the PhD student of the year from St Andrews. I believe she's had some family issues and she may not be able to make it. But your events manager, Chris Stratton, he's got it all in hand. He's looking for a replacement speaker. So I'll keep you updated once we know who that's going to be. Okay. So with that, I'd like to thank Oliver for his fantastic talk on the exoplanets and how crusty they are, and all the information that comes from that. Rich for handling the Q&A so well, Mick for your Sky at Night, Stuart for your space news, and also all you good people for coming along tonight and joining in with us. It makes it all worthwhile. So that's it from me. So for those of you I don't see in the gathering in a few minutes, hopefully I will see you next month. And when I say see you, I mean see you, properly see you on the 12th. Okay. So good night from me and keep looking up, everybody.